So this concept that we've just explored of phase, phase shift, and phase interference has some important implications when we begin talking about our next topic, which is tones and timbre. So we define simple tones as a tone that has only one frequency component. In other words, it's a sine wave. And we can hear an example of what a sine wave sounds like here. Complex tones have more than one frequency component present. Complex tones can take a lot of different forms, and we'll talk about those in a few moments. However, we want to make sure that we understand a simple tone has only one frequency component, so we can represent it as a single sine wave. Complex tones will have more than one frequency present. So we want to take a moment and talk about this idea of frequency spectrum. Again, a sine wave contains a single frequency, but there are other types of waveforms that have periodicity, in other words, they repeat periodically, but they have different shapes. And we're going to take a minute and I'm going to play each of these for you. This is a sine wave. This is a square wave. This is a triangle wave. This is a sawtooth wave. Now in each case, you likely heard a pitch, and that these were all the same pitch. And we heard it as changing timbre. But I want you to take a moment as I switch between sine wave and square wave and notice that what's really changing is actually the presence of additional frequencies that are higher than what you're perceiving as the pitch. Square waves, triangle waves, and sawtooths are examples of complex waves. So, complex tones consist of multiple frequencies. In some cases, those frequencies can be harmonically related. What that means is that they're a whole number multiple of the fundamental frequency. So if we had a tone where the fundamental frequency was, say, 220 hertz, which is A3, and sounds like this, we would find that the harmonics are whole number multiples of 220 hertz. So they might occur at 440 hertz, 660 hertz, 880 hertz, etc., as we take 1 times 220, 2 times 220, 3 times 220, and so on with whole numbers. We can also have non-harmonically related partials. In other words, we may find that the frequencies of a complex tone are not related by whole numbers, and we would call these non-harmonically related partials. So a complex waveform can be broken down into combinations of many simple waves, and we call these partials. So in this case, we can see a waveform at the top of our screen, represented in blue. In the middle part, we can see that this frequency has been separated into two separate frequencies. One at 300 hertz, one at 500 hertz. Let's take a moment and let's listen to what this sounds like. Here is the complex tone. Here is the 300 hertz portion. Here is the 500 hertz portion. And here they are together, creating the complex tone. So this leads us to a concept called timbre. Timbre is the perceived sound quality of a sound source, and it's generally viewed as the result of two physical characteristics of the sound source: its frequency spectrum and its envelope. Now, real-world sounds get very complex, with many frequencies or partials presented at different times, each with their own dynamic envelope. So some of those partials may be harmonically related, but many might not be. So real-world timbres can become quite complex and often include many partials that are not a part of the harmonic series. So frequency spectrum can be divided into harmonically related partials. Again, these are any partial that is a whole number multiple of our fundamental. And then we can have non-harmonically related partials. This could include what's called inharmonicity. Inharmonicity refers to harmonically related partials that deviate from a perfect whole number multiple. In other words, we hear that there's a harmonic that's almost a whole number multiple of the fundamental, but it's slightly out of tune. This actually happens quite often in real world construction, and in some cases, with instruments like bells and some percussion instruments, it's done intentionally. We also find that, for example, in the human voice, there's something called a formant. This is the result of how we shape our mouth and is how we distinguish between different vowel sounds regardless of what frequency or pitch we're speaking at. Whether I say an E or E, some frequency components remained the same, which gave it that essential E-ness. Those frequency components do not change or follow the fundamental. So these are called formants. We have related concepts that happen with various types of sound sources that generally result from the resonance of various parts of the sound source. For example, an acoustic guitar will have pitch content and harmonically related partials related to the length and tension of the string, producing a fundamental frequency, and also producing harmonics. However, the sound of an acoustic guitar also includes the resonance of the body, the resonance of the soundboard, the resonance of all of the various vibrating parts of the instrument that do not change regardless of what note we play on the guitar. And it's this combination that give us the really distinct frequency spectrum of a guitar or a clarinet or a piano or any other sound. Now, sounds in which harmonic partials are prominent will tend to have a recognizable pitch, and we'd say that these are tonal or tone-like sounds. However, we can have other sounds that have mostly non-harmonic partials, or the harmonic partials just aren't prominent at all. Those will tend to have a more noise-like quality. We might expect to hear something like this. When we hear that sound, there isn't a single frequency that we would sing to say, yeah, that's the pitch of that. We would say that that was a noise-like sound. Now, in real-world sounds, we find we're very rarely perfectly tone-like, but we're also often not all the way to noise. So we talk about a continuum between tone-like sounds and noise-like sounds, and we talk about where on that continuum a particular sound might occur. For example, a sound might be pitched but still have some noise-like qualities, or a sound might be very noise-like but have a bit of a pitched quality to it. The other key characteristic of sound related to timbre is the envelope, and we can go back to this ADSR curve, or attack, decay, sustain, release curve that we looked at earlier. However, the important thing is, now that we understand that a real-world sound might have many different frequency components, the important thing to understand is that every partial will have its own dynamic envelope. Sometimes the dynamic envelopes between partials are related or coincide, but often they don't, which is what gives real-world sounds a changing characteristic or a changing timbre over time.